Let's dive right into this explainer on the truly fascinating mechanics of extracting water from the ground. We turn on a tap and water just flows, but the invisible mechanics making that happen rely on some incredibly dynamic principles of hydrogeology. We're going to map out exactly what happens in the dirt, rock, and water beneath us the second a pump is switched on. Here's our agenda for today. 1. The hidden underground world. 2. Classifying wells and aquifers. 3. The cone of depression. 4. Rules of radial flow. And finally, 5. Testing the waters. Section 1. The hidden underground world. To really get this, we have to look way past what we can see on the surface. So what actually happens when we pump water from the ground? It seems like a perfectly simple question, right? But the physical consequences of turning on that pump are actually pretty dramatic, completely invisible to us, and they happen on a massive scale. It's really not just a matter of a pipe sitting in some underground lake. Think of it like the classic straw in a milkshake effect. Before any pumping happens, you've got this perfectly flat, static water table. But the moment that pump kicks on, it literally drags the water table down around the pipe. The entire shape of the groundwater completely transforms, bending to flow radially right into the well. Section 2, classifying wells and aquifers. Before we dig deeper into the physics of that bending water, let's categorize the different environments engineers are actually dealing with out in the wild. The way we design wells is entirely dictated by the geology. For instance, in shallow, unconfined layers, we traditionally use massive, large-diameter dug wells. Some of these were even built by hand back in the day. But for those deep, confined aquifers, that's where we bring in the small-diameter tube wells. The depth and the pressure totally dictate the entire engineering approach. The really crucial point here is the physical difference in how these specific aquifers react to pumping. In an unconfined aquifer, which is kind of like a giant wet sponge sitting in a bowl, pumping physically drops the actual water table. But in a confined aquifer, the water is trapped between hard rock layers and it's under intense pressure. Pumping here rapidly drops what we call the piezometric surface, so you're dropping the pressure level rather than just emptying a physical space. All right, Section 3, the cone of depression. Let's get to the climax of the story and define the absolute most important hidden mechanic in hydrogeology. First up, we need to talk about drawdown. Drawdown is simply the drop in the water table elevation from its normal resting level. Think of it as creating a localized hydraulic gradient, basically a slope that literally uses gravity to force water to flow from the surrounding soil right into the well. With that drawdown, the water, it just sits there doing nothing. And that drawdown doesn't just happen in a perfectly straight line. Assuming the earth around it is uniform, sucking water up the well creates this invisible three-dimensional funnel in the water table. We call this the cone of depression. And as you keep pumping, this cone gradually expands outwards and goes deeper, pulling in water from further and further away. You get this expanding cone geometry in both unconfined and confined aquifers. The continuous expansion of this cone is exactly how the well sustains its flow. And the absolute farthest edge of this cone, the exact horizontal point where the drawdown hits zero and the water table is back to normal, is a highly vital measurement known as the radius of influence. Which brings us to Section 4, rules of radial flow. So we understand the physical shape, but how do hydrogeologists actually calculate these invisible forces? Let's talk about the math behind the magic. We're definitely not going to get bogged down in the complex algebra right now, but it's super fascinating to know that engineers use tools like Sichart's formula to estimate that exact radius of influence. By taking the drawdown and multiplying it by the square root of the soil's permeability, they can calculate exactly how far a well's invisible reach extends underground. But here's the catch. To make those elegant equations actually work, engineers have to assume 7 perfect world rules. They have to assume the aquifer extends infinitely, that the soil is perfectly uniform everywhere, the initial water table is flawlessly horizontal, and that the water flow remains totally smooth and purely laminar. It's a mathematically perfect scenario that gives them a solid baseline to work from. Section 5. Testing the waters. Now, of course, the real world is messy, and geology is highly unpredictable. So let's rise back up to the surface and see how professionals verify these perfect world assumptions. They do this by running a pumping test. A crew will pump water out of a well at a strictly constant rate. We're talking often for 24 to 72 hours straight, carefully measuring the drawdown. But the absolute most crucial step, that happens when they finally stop the pump, and meticulously observe the water level's recovery back to its normal state. So why is stopping the pump so important? Well, measuring those changes after the system shuts off is vital to confirming all that math. A rapid recovery phase proves the underground system has high productivity and storativity. It basically tells the engineers, hey, this aquifer is healthy and can totally handle the stress of continuous pumping. And avoiding overstressing the system is absolutely paramount. If we extract water way too fast, we cross a dangerous threshold called the critical yield. At that point, the water velocity becomes so intensely high that it actually dislodges soil particles. This leads to something called sand pumping, which degrades the water quality and can literally cause the entire well structure to collapse and fail completely. No way do we want that. To prevent total disaster, engineers establish a safe yield. They take that critical failure point and divide it by a massive safety factor, usually 2.5 to 3.0. By doing this, we keep these invisible mechanics completely stable, ensuring the well doesn't fail and that our water supply lasts for generations. So the next time you turn on your tap, you've got to ask yourself, just how big is the invisible cone of depression growing beneath your feet right now to bring that water to you?